Hello everybody. For my final project, I will be working on enhancing GPS localization in urban settings. One of the main sources of GPS positioning error in urban areas is multipath interference, which is basically where signals from GPS satellites reflect off buildings or other large structures, which confuses GPS-enabled devices. I first noticed this problem when I started to record runs with a GPS watch and upload them to Strava, which is kind of a common fitness tracking website which allows you to visualize the route that you took. Whenever I ran near tall buildings, my watch seemed to do a very poor job of estimating my location. So the plot above, or the screenshot above, shows this. So I knew that I ran along 71st Street, which is the blue line, but the actual position measured by my GPS watch on the way out and back is shown with these red lines. And in some places, the error between the actual path and the measured path was greater than 15 meters, which is pretty bad even for commercial GPS-enabled devices. My solution to this problem is to implement a particle filter, similar to the ones we designed in Lab 4, with one significant addition. Instead of just using sensor measurements from the GPS to calculate particle weights, I will also be using information from a database of known street locations. So my particle filter will weight particles that are on or very near known streets much higher than particles that are not. I've not yet settled on a motion model or particle state, but I'm leaning toward a particle state of just position, heading, and forward velocity. The motion model could be made pretty elaborate if I wanted to do things like increase the probability of turning near intersections, but those will probably just be stretch goals if I have time. I'll be using openstreetmap.org for the street location database. This is actually the same kind of service that's used by Strava and a lot of other applications. It's pretty straightforward to download all the information that I need for even an entire city, but the information is encoded in kind of a hard to parse way. It actually is in its own language, the overpass query language, which I'm not familiar with and will potentially be kind of time consuming to learn how to parse and get into a Python array or dictionary. In the worst case, I can kind of manually create my own database of street locations. If I know the route that I'm going to be taking beforehand, I can just do that with Google Maps, but I'd prefer not to do that. Data collection will be done with a Garmin GPS watch, and I've already gotten the data flow up and running for that. This was a little bit tricky because Garmin watches stored their localization information in a proprietary binary file format called a .fit file, or a fit file, and decoding them was kind of a pain. But the plots on the right show that I was able to plot the same path in Python, so the plot on the left here, as Strava was able to produce. And I'm still working on getting a map in the background of my Python plot. Conducting experiments and assessing performance is pretty straightforward for this project. I'll first plan a known path using Google Maps. You can basically drop kind of pins at various points along the path that you want to take and get the exact latitude and longitude. Next, I'll record a run or a walk on the path with the GPS watch. I'll download the produced fit file and process that. And then finally, I'll run my modified particle filter over the data using, again, that draws from this database of known street locations. To compare the accuracy of the filter versus the unfiltered position estimation, I'll be using the equation shown here on the bottom. This is actually the same equation that we used in labs 3 and 4 to calculate the RMS error. And basically it calculates how far away the estimated position is from the nearest point on the known path, or the kind of absolute truth path. And averaging that error over the whole trial is a pretty good estimate of the position accuracy. Thanks for listening. Are there any questions?